US Physics Olympiad year 2022 USAPHO final round. Problem A3. Rainbow road. In geometric optics, a caustic is a bright curve of light that appears when many incoming light rays are focused in the same outgoing direction. The most famous example of the caustic is a rainbow, which occurs when light interacts with the spherical water droplets. Consider a spherical liquid droplet of radius r with the index of refraction 1 less than n less than 2, suspended in air with index of refraction n equal 1. Question A. Consider a light ray that enters the droplet with the impact parameter b, reflects one of the inside surface of the droplet, then exits, as shown at the left below. Give your answer in terms of the dimensionless impact parameter x equal b over r. Hint: the four marked angles are congruent. First, find the angle by which the light ray is deflected at the first refraction. Second, find the angle by which the light ray is deflected at the reflection. Third, find the angle by which the light ray is deflected at the second refraction. The sum of these three quantities is the net deflection angle phi as a function of x. The light can also reflecticide more than once or never either at all, but for simplicity we will ignore these other paths. Question B. Next, we consider when caustics form in general. Suppose the droplet is uniformly illuminated by parallel light rays of intensity I0 and sits at the center of a spherical screen of radius big R much greater than small r, as shown on the right above. Consider the light that enters near dimensionless impact parameter x0 and exits near angle phi0 equal phi from x0. First, what is the power incident on the droplet of x0 less or equal x less or equal x0 plus dx? Second, what is the area on the screen illuminated by the outgoing rays at phi0 less or equal phi less or equal phi0 plus df? Third, a caustic occurs when the intensity of light on the screen diverges. Assume that phi0 not equal 0 and phi0 not equal pi. Under what conditions does the light incident at x0 lead to a caustic at phi0? Express your answer as a condition on the function t from x. Question C. Find the angle phi0 of the rainbow in terms of n. Hint: the derivative of arcsine is 1 over square root from 1 minus x squared. Question D. For water, the index of refraction of red light is 1.331 and the index of refraction of blue light is 1.340. Find the angular width of the rainbow on the screen and give your answer in degrees. Question E. A glory is an optical phenomenon which involves light scattered directly backward at phi equal pi, leading to an apparent halo around the shadow of an observer's head. For what value of n is there a caustic at phi equal pi? Can glories from water droplets be explained in terms of caustics? Solution for question A. Consider a light ray that enters the droplet with the impact parameter B, reflects once of the inside surface of the droplet, then exits as shown in the picture. Give your answers in terms of the dimensionless impact parameter x equal b over r. Hint: the four marked angles are congruent. First, find the angle by which the light ray is deflected at the first reflection. Solution: the angle the incoming light ray makes to the normal of the droplet is θ1 equal arcsine x. By Snell's law, the angle to the normal inside the droplet is θ2 equal arcsine x over n. The first refraction causes a deflection of θ1 minus θ2 clockwise. So that was the answer for question I. Second, find the angle by which the light ray is deflected at the reflection. Solution: the reflection keeps the angle to the normal the same and causes a deflection of 2 pi minus 2 θ2. This was the answer for the question II. Third, find the angle by which the light ray is deflected at the second refraction. Solution: at this point the angle to the normal is still θ2, and by Snell's law it reverts to θ1 outside the droplet. This causes a deflection of θ1 minus θ2 with the same sign clockwise as in part I. Thus, we conclude the total deflection angle as a function of x, phi x equal 2 pi minus 4 θ2 plus 2 θ1, or this expression 2 pi minus 4 arcsine x over n plus 2 arcsine x. That was solution for question A. Solution for question B. Next, we consider when caustics form in general. Suppose the droplet is uniformly illuminated by parallel light rays of intensity I0 and sits at the center of a spherical screen of radius big R much greater than small r, as shown at the picture. Consider the light that enters near dimensionless impact parameter x0 and exits near angle phi0 equal phi from x0. First, what is the power incident on the droplet at x0 equal or less x and x equal or less x0 plus dx? Solution: the region with the impact parameters in this region is a thin annulus with the radius rx0 and the cross-sectional width r dx. Then the area of this annulus is this one, 2πr square x0 dx, and the power is I0 ds, or 2 pi I0 r square x0 dx. That was solution for the first one. Second, what is the area on the screen illuminated by the outgoing rays at phi0 equal or less phi and phi equal or less phi0 plus d phi? Solution: by similar reasoning to the previous part, we have radius of illuminated area on the screen is big R sine phi 0, and the cross-sectional width is R delta phi. So the total area will be 2 pi big R square sine phi 0 d phi. That was a solution for second. Third, a caustic occurs when the intensity of light on the screen diverges. Assume that phi 0 not equal 0 and not equal pi. Under what conditions does light incident at x0 lead to caustic at phi 0? Express your answer as a condition on the function phi from x. Solution. By dividing our two answers, first one by second one, we will find intensity on the screen is delta P over delta A, which is I0 small r square by big R square multiplied by x0 over df over dx multiplied by sine phi 0. This diverges when the denominator becomes 0, which in this case only occurs when first derivative of phi by x in point x0 equals 0. That is, caustic will occur at this condition. Intuitively, this condition means that a broad range of incoming light rays and up focused on a narrow curve on the screen. So this is the condition for caustic, and this was the answer for the third one. Solution for question C. Find the angle phi 0 of the rainbow in terms of n. Hint: the derivative of arc sine x is 1 over square root from 1 minus x square. Solution. The condition for caustic is phi prime equals 0. From here we have this equation which gives us 4 multiplied by 1 minus x square equal n square minus x square. From here we have x equal square root from 4 minus n square over 3. And finally we can put this x to our expression for phi, and the result will be phi 0 equal this expression. That was solution for question C. Question D. For water, the index of refraction of red light is 1.331 and the index of refraction for blue light is 1.340. Find the angular width of the rainbow on the screen and give your answer in degrees. Solution. Substantiating these two indices of refraction into the above equation and subtracting the results yield angle will be 1.30 degrees. That was solution for question D. Question E. A glory is an optical phenomenon which involves light scattered directly backward at p equal pi, leading to an apparent halo around the shadow of an observer's head. For what values of n is there a caustic for phi equal pi? Can glories from water droplets be explained in terms of caustics? Solution. Referring to our answer above, we have a caustic whenever the denominator df over dx multiplied by sine phi, denominator d phi over dx multiplied by sine phi vanishes, and the sine phi vanishes for phi equal pi. Therefore, we will have a caustic at phi equal pi as long as light can be reflected backwards at all. It means whenever there is a solution for phi x equal 0, that is because at this angle all the outgoing light is directed at a single point on the screen. We thus need to solve arcsine x equal to arcsine x over n. Taking the sine of both sides and using the double angle formula gives this equation. Solving for n, giving n equal the square root. As the impact parameter x yielding the backward caustic range from 0 to 1, the values of n ranges from a maximum of 2 to a minimum of square root from 2. The index of refraction of water is outside this range, so glories from water droplets cannot be explained in terms of caustics. The reason glories are visible is still under debate. So that was solution for question E, and here we finished discussion for problem A3.